Hello friends, welcome back to our YouTube channel. If you like this video, please like, share and subscribe. I'll share our videos commanded by our experts, so let's begin.
If you like, please like, share and subscribe. So let's begin our today's topic. Let's begin.
SpaceX is preparing to go public, pivoting its core business from rocket launches to the provision of vertically integrated AI infrastructure. This S-1 filing outlines a targeted valuation of up to $2 trillion, aiming to raise between $50 and $75 billion under the ticker SPCX. The prospectus details an argument for moving the physical compute stack off-planet to bypass the resource constraints found on Earth. The logic centers on the rapid acceleration of large reasoning models and autonomous AI agents. The scaling of these networks is no longer limited by the speed at which foundries can print silicon chips. The actual constraints are physical: acquiring sufficient land, drawing enough sustained power from an aging electrical grid, and sourcing the immense volume of water required to cool thousands of closely packed servers. SpaceX intends to solve this by relocating the hardware stack into low Earth orbit. Investors are being asked to buy into a specific premise that the most reliable place to scale artificial intelligence is in the vacuum of space. Running these massive gigawatt-scale AI training clusters here on Earth requires an immense, continuous draw of baseline electrical energy. Because regional power grids experience natural fluctuations and occasional deficits, operators are forced to build massive, expensive lithium-ion battery backups to prevent system failures during a compute cycle. Once consumed by tightly packed GPU arrays, almost all of that power is converted directly into heat, creating a severe thermal management crisis. Keeping those chips from melting requires active HVAC convection systems, which consume millions of gallons of localized water and require their own secondary electrical supply just to run the pumps and fans. This conceptual schematic illustrates how these input requirements scale linearly with compute demands until they hit an unbreakable capacity ceiling. Expanding the footprint to spread out this thermal load requires buying vast tracts of real estate, aggressively driving up capital expenditures. Scaling terrestrial architecture on this trajectory eventually results in a mathematical break, where the inputs required exceed the local environment's ability to provide them. The orbital architecture circumvents the terrestrial grid by relying entirely on direct solar irradiance. This 3D model demonstrates the required geometric trajectory, known as a sun-synchronous orbit. As the Earth rotates on its axis beneath the satellites, the orbital plane remains fixed facing the Sun, allowing the hardware to avoid entering the Earth's shadow. In this specific polar path, the data center modules receive uninterrupted solar energy over 99% of the time. Terrestrial solar farms lose generation capacity every night and suffer severe efficiency drops during weather events. Constant orbital exposure removes the need to launch heavy, expensive battery modules to cover downtime, streamlining the payload. By removing the variable of planetary rotation, sun-synchronous geometry turns solar irradiance into an absolute, baseline energy source capable of sustaining continuous compute cycles. Sourcing the power solves the first constraint, but it immediately introduces the second, managing the intense heat output of active AI nodes. Traditional convection systems rely on circulating air or liquid to carry heat away from processors, a mechanism that is physically impossible to execute in the vacuum of space. To prevent the processors from overheating, the satellites utilize passive radiative cooling. Instead of pumping chilled liquid across server racks, the orbital module routes thermal energy into massive radiation panels. These panels bypass external water supplies entirely, dissipating the thermal load as infrared radiation directly into the absolute cold of the surrounding vacuum. This architecture has drawn heavy skepticism from space sustainability experts. The primary engineering risk is that ambient radiation in low Earth orbit will rapidly degrade sensitive silicon circuitry, causing high failure rates among the AI chips. When hardware fails, performing complex physical repairs or swapping out corrupted microprocessors while maintaining orbital velocity introduces severe logistical delays. Despite the harsh environment and maintenance hurdles, passive radiative cooling remains the only physical mechanism available to bypass the water limits capping terrestrial server expansion. Establishing this infrastructure requires solving the logistical hurdle of lifting thousands of tons of dense server racks into orbit. The required mass transport is enabled entirely by the heavy lift capacity of the Starship launch vehicle. The prospectus points to a specific economic inflection point. Starship is engineered to reduce historical payload-to-orbit delivery costs by over 99%. This scalable constellation model demonstrates the end goal: to launch and link 100 gigawatts of total compute capacity into space annually. Achieving that metric will require building out a modular constellation consisting of up to 1 million dedicated computing satellites operating in tandem. The immediate roadmap for this build-out is organized around the Colossus hardware architecture. The first generation of 100 kilowatt test nodes is scheduled for deployment as early as 2028. By structurally compressing these massive launch costs, Starship takes the concept of orbital data centers out of the realm of theoretical physics and turns it into a mathematically sound infrastructure rollout. The engineering models are now backed by the hard financial realities detailed in SpaceX's first-ever public ledger. The filing officially consolidates the SpaceX launch division, the operational Starlink network, and the newly integrated AI division into a single corporate structure. The consolidated books show $18.7 billion in revenue for 2025, largely driven by $11.4 billion from Starlink, balanced against a net loss of $4.9 billion. That net loss is tied directly to a $13 billion capital expenditure investment, specifically targeting new AI infrastructure. The market is already pricing in demand for this off-planet compute, highlighted by Anthropic signing a $15 billion annual agreement for direct access to the orbital data centers. Google is validating the approach internally through Project Suncatcher and has entered into launch partnership talks with SpaceX for its own AI hardware. But the underwriter's prospectus also includes 70 pages of risk factors, many of which focus directly on corporate governance. The IPO utilizes a dual-class share structure that grants Elon Musk an 85.1% hold on the cumulative voting power. This equity structure legally classifies SpaceX as a controlled company, completely exempting the entity from standard corporate board oversight and shareholder interventions. The Orbital AI infrastructure designed to solve the terrestrial compute bottleneck is not being built as a public utility. It is being established as a privately monopolized grid under absolute, singular control. The aerospace industry is preparing for the largest initial public offering in history, led by a company repositioning itself as an orbital infrastructure titan. SpaceX has officially filed its S-1 registration statement with the SEC. They're targeting a valuation between $1.75 and $2 trillion, with the aim to raise up to $75 billion in capital. The prospectus defines SpaceX as a vertically integrated AI and orbital compute infrastructure company. This pivot addresses a strict physical wall rapidly approaching the technology sector, the terrestrial AI bottleneck. The scaling of large reasoning models and autonomous agents is reaching a point where the primary limiting factor is no longer the rate of silicon manufacturing. The real constraints are rooted in terrestrial geography. Data centers require immense tracts of land, massive power grid connectivity, and vast amounts of water to maintain thermodynamic cooling limits. Opening its financial books to the public for the first time, SpaceX revealed that in 2025 it poured $13 billion into AI infrastructure, predominantly funding massive mega GPU clusters known as Colossus 1 and Colossus 2. The S1 document presents a specific thesis. To achieve and sustain gigawatt-scale AI compute, moving the physical server stack off-planet is the only mathematically viable long-term solution. This upcoming public debut is a massive financial bet on owning the physical infrastructure of the AI revolution by escaping Earth's thermodynamic limits. Running millions of GPUs requires a continuous draw of megawatts, tying terrestrial data centers completely to the capacity and limitations of the traditional power grid. Terrestrial renewable energy suffers from intermittency. Data centers must build massive, expensive battery backups to maintain constant power through the night or during weather events. SpaceX's orbital architecture solves this intermittency directly. The strategy relies on deploying these satellites into trajectories known as sun-synchronous orbits. By calculating precise altitudes, they ride the Earth's terminator line. They maintain continuous line of sight with the sun, avoiding shadows. These nodes receive uninterrupted solar irradiance 99% of the time. There is no night cycle and no cloud cover. The massive capital expenditure required to build and replace heavy chemical batteries on the ground is eliminated. Moving data centers to these orbits transforms energy generation from a grid-dependent terrestrial liability into a continuous, battery-free physical asset. Power generation is only half the equation. The second severe bottleneck for terrestrial AI is the immense thermal output generated by these mega GPU clusters. On Earth, dissipating that heat requires highly complex HVAC systems that consume millions of gallons of water and create a tremendous secondary draw on the electrical grid to run pumps and fans. Because space is a vacuum, there is no ambient air to blow across a heat sink to cool a server down. Conduction and convection fail in a vacuum, which necessitates a different thermodynamic approach. To solve this, SpaceX relies on passive radiative cooling. Thermal energy is collected from the chips, routed to the exterior, and dissipated directly out of the fins as infrared radiation. Utilizing the near absolute zero temperatures of deep space as a heat sink requires absolutely zero water consumption. It also requires zero active electricity for cooling, which optimizes the power usage effectiveness of the data center. Every watt generated goes toward compute. The vacuum of space provides a mathematically perfect, zero-cost heat sink for gigawatt-scale operations. The physics of orbital energy and thermal dissipation have been understood for decades, but the model remained theoretical due to a strict financial barrier. Historically, the cost to launch heavy payload mass, like dense server racks, into orbit was financially prohibitive. The Starship launch vehicle is the technical requirement for this entire orbital strategy. Starship is designed to cut orbital payload delivery costs by over 99% relative to historical aerospace averages. As space access costs plummet and terrestrial power and land increase, the two lines intersect. Here, orbital server deployment becomes financially sound. The S1 outlines an immediate timeline, noting that early-generation 100-kilowatt test nodes are expected to launch as early as 2028. From there, the company targets an ultimate capacity goal of launching 100 gigawatts of compute to space every single year. Achieving this requires deploying up to 1 million dedicated computing satellites, organized into modular orbital shells around the Earth. Starship provides the economic bridge to make orbital data centers a deployable corporate asset. The S1 details a strategy consolidating SpaceX's rocket division, the Starlink satellite fleet, and the integrated AI operations into a single entity. Through a dual-class share structure, Elon Musk maintains authority over the public entity, retaining 85.1% of the cumulative voting power. Major technology players are already committing capital to this infrastructure hypothesis. Anthropic has reportedly entered into an agreement to pay SpaceX $15 billion annually for exclusive data center access. Google is validating the thesis via Project Suncatcher and has held talks with SpaceX regarding launch partnerships for future AI hardware. Despite these capital inflows, space sustainability experts maintain skepticism over the realities of operating silicon in low Earth orbit. The ecosystem faces three major operational threats: high-velocity orbital debris, the radiation degradation of microchips, and complex hardware repair logistics thousands of miles from the nearest technician. But overcoming these engineering hurdles would allow SpaceX to capture the foundational layer of AI compute capacity for the globe. SpaceX's $2 trillion valuation represents a bid to own the off-planet infrastructure that will dictate the future of intelligence on Earth.